Hi everyone, and welcome to this video. Today I'm going to be talking about my NEM Relay models. In particular, I'm going to be talking about the Comsol model and how you can generate the layout for a NEM Relay, which we can use with Comsol. So this is kind of what the relay looks like. You can see it, how it works. Basically, it's a clamped relay model, and it moves up and down in the Z direction, and will connect two terminals or more that are on the surface of the substrate that you're modeling. And so I'm going to show you how you can create this kind of model in Comsol and then do several different studies on that model. So the first thing that you want to do is, so firstly, this model works with Comsol 5.4, and also uses, so it also requires the MEMS module and the ECAD import module. So firstly, let's talk about how to generate the KLayout design. So basically, my NEM Relay model basically is split into two parts. So one is the 2D design, right? So you're basically building this description of the NEM Relay in 2 dimensions, the XY dimensions. And then in Comsol, you do the 3rd dimension, which is basically how do you extrude those 2-dimensional designs into a 3rd dimension. And so let's start with how to generate the KLayout. So first, you should clone this repository. The link will be in the description of this YouTube video. And basically, so once you've cloned the repository, you can go take a look in the layouts directory in the top level of the repository, and there should be a file called relay.py. So this is the model, and also if you have KLayout, you can actually view the outputs of this. So I'll show you first what the output looks like. And actually, that'll be helpful for understanding what the model is doing internally. So this is a parametric layout generator, which means that it actually allows you to change the dimensions of the 2D model. So what I'm going to do is go into layouts and do open relay.gds. And so GDS2 is a format that's standard for CAD layouts. And we're going to import this into Comsol later, which just makes our lives a little bit easier. And I'll get to that in a moment. But first, let's talk about how to generate the actual layout. So here's what the layout looks like. So I'm going to open relay.gds. It should open in KLayout if I'm not mistaken. So KLayout is a really cool tool that allows you to make these sorts of parametric layouts of your design. And so here it popped up on my screen. And so you can see that there's several different layers, right? So let's go through what all the different layers are doing, right? So, and you kind of need to have an understanding of how a NEM relay works in order for this to make any sense. Maybe it's in view layers. So if you go to view layers, you should be able to see that there are different layers. And what I'll do is I'll turn on each one at a time so we can see what each one does. So, so basically, well, firstly, let's talk about these 4 corners, right? So we see these 4 corners here. Those are called the anchors. So the anchors of the relay are what keep them clamped sort of to the surface of your substrate, right? So basically, when you're building these relays in practice, what you'll be doing is you'll be fabricating them on some material. And these anchors are what keep the relay connected to the material. And you can see here kind of how that works, right? So the anchors are basically what's holding this whole thing down. They're like the parts that stay, and they don't move. These anchors don't move. The part that moves is the relay body. Okay, so let's get started. So let's show only selected. So we'll first show this. So the first layer right here is the anchor layer. Now I'm going to only show the second layer. So these ones are called the channels. So the channels are basically, the way NEM relays work is when they get clamped down, they basically connect 2 terminals. And this channel basically acts as a wire between these 2 terminals. And that's really useful. So these kind of have been laid out in this particular shape for reasons that I'll discuss later. Then these right here, these are called the contacts. So this basically later we'll see a sort of a side view of the relay once we go into Comsol. And the contacts basically are the parts that touch down onto the surface of your substrate where you have landing pads, what we call landing pads. And those landing pads actually can connect to other circuitry in your system, right? So they're basically, this is what this would be the source and the drain of the NEM relay. So let's move on to the next one. This right here is the body of the relay, right? And so the body of the relay is sort of suspended, right, by these anchors. And you can see that there are different components of the body. So I'm just going to define those here. So these right here, these are called the beams. The beams are basically the things that lower the spring constant of the NEM relay and allow it to go up and down. But more importantly, they allow it to go back up, right, once you've pulled it down. And then the body, this part, so this is we're dealing with electrostatic relays here. So it's actually the electrostatic force between the relay plate, right? The plate being this sort of like the square part in the middle, and the gate, so the plate and the gate. The gate is basically something that sits on the bottom of the relay, right? And attracts it downwards, basically. So it's attracting the relay downwards. And so it's basically this Coulomb force that's acting between these two components that allows you to move the relay up and down, right? And so, yeah, so this is the relay body. So let's move on to the next one. These right here are holes. So these are just, if you go back to the, if you go to the, this picture here, you can see that there are a bunch of holes. And these holes have two purposes in a real NEM relay. So the first purpose is during fabrication. These holes allow you to remove the material that's in the middle between the relay and the substrate, right? So between the body and the bottom, the substrate, right? The second reason is that these holes allow for gas molecules, namely air in our context, to escape through these holes, basically, when the relay is going down. And that actually will speed up the operation of the relay, so that it doesn't, like, it's not pushing the air out of the sides instead. So the air can actually come through those holes. Yeah, these are really important design features for a real NEM relay, which you would be trying to fabricate. So let's move on to the sixth layer. So this layer right here, so we'll show only selected here. So this is basically part of the metal layer that's on the bottom, right? So we can see that there's the middle square, right? This is actually the gate. This is where this is like the gate contact, right? So the gate is this big metallic plate that we have that's attracting the NEM relay downwards. And then we also have contacts for the anchors, right? And these will usually be grounded or will be body biased at some potential. So you can set the voltage for these terminals to whatever you'd like them to be set to. And they should be at the same, they should all be at the same voltage, right? Because they're all connected to each other through the body of the relay. So let's talk about the seventh layer now. So, so let's show only this one. So these right here are part of the landing pads, right? So we want the relays to come down and make contact with this NEM relay at some point, right? And we need the sources and drains to come into contact. So in this model, you can sort of parameterize the number, like how many contacts there are, but in this case, we're dealing with 16 contacts corresponding to 8 sources and 8 drains. So actually this model is designed for multi-pole NEM relays, which basically can connect to multiple signals at the same time. And then lastly, we have, so let's show only this one. So, okay, so this one right here is actually the dielectric spacer. So sorry, let's go back to this one. This is the dielectric spacer between the landing pads and the gate, right? Because you need to, otherwise they'll be shorted. And you don't want your source and drain to be shorted to your gate. So you need to have some spacer between them. And then these ones, this last layer, is the actual landing pad. So this is where the relay comes down onto it. If you don't know exactly what all of this means, I'll explain it more when we go into the Comsol model, because it's easier to see it once we go into 3D. So this is kind of the 2D layout of what this is. And now I'm going to show you how we can actually generate this, and we can modify parameters to make this relay do different things. So the first thing I'm going to do is explain KLayout. So let me make this larger so that everyone can kind of see the text on this a little better. So, so basically the way this model works, I have this open in Visual Studio Code, and you can see that there are, at the top there, we first import the math library for Python and the KLayout library, which is called PyA. Then what we do is we define the relay parameters. And these are things that you guys can modify to your own design specifications. You can also modify the way the layout is done completely. So if you don't like the exact design that I've come up with, you can change it. You can change the number of contacts, etc. But so the things that we have here are, we have the number of polygon sides, right? So here we have 4. In this context, I don't think I've actually used this anywhere, but if you wanted to change the number of sides of the polygon, like for example, if you wanted to use a hexagonal design or a pentagonal design or a triangular design, you could modify this parameter. I don't think it does anything yet. Oh, it's used in a couple of places, basically for the rotations. It'll divide it. It'll basically use this to figure out the angles that it should rotate by. In this case, it would be 90 degrees. So yeah, we're working with a square plate right now, but you can obviously modify this model to do other things. Actuation gap, I don't think this is used anywhere. So this one, yeah, so this is not used anywhere because this isn't really part of the relay design. It's just in here. But yeah, so the thickness of the poly layer, we don't care about this. This is also another 3D parameter, right? This is the Z direction. So this one I don't think is used anywhere as well. Yeah, I should probably get rid of these in this model. So I'll probably do that after I record this. So then we have the length of the side plate. By the way, these are all in units of nanometers. So this is basically the length of, I'm just going to show all layers. It's basically the length of the side length of this relay. So then we have the cantilever, right? So the cantilever are these beams, right? We have these beams sticking out. Another term for them is cantilever. That basically is the length from here to, it's one of these, it's like the length from here to here or something like that. But anyway, sorry, it's the length from here to here, because it's exactly the same as the length of the plate in this context. And then the width of the cantilever is 200 nanometers. So you can see that that's how we decide how thick this is. And then we have the gap between the plate and the cantilever. So this is exactly the same as the width, right? So we can see that there's a gap here between the cantilever and the plate. And that's what we can see going on here. So then we have the side length of the via. So the vias are the same as the anchors. You can just think of those as being the anchors. And these are, the reason I call them vias are because they go down to the substrate and they are kind of the connection that connects these two different layers, right? And so the side length of that is 400 nanometers here. Then we have the anchor attachment. So that's this attachment that goes around, right? And that is the same length as the via plus 200 nanometers. And so right now we have circular contacts. So basically they're basically arranged in a circular. So this basically just tells you the radius. This basically tells you that it is operating in the circular mode. N contacts, N is basically the number of contacts. This is the side length of each contact. So here we have 16 contacts. So you can see that there's 16 of them. The side length of each contact is basically the side length of these squares. The radius of the circle along which to place the contacts, that basically, you can see that there's a circle here and there's some radius that's being placed. And then we have the thickness of the contact. This we don't use anywhere here, but we'll be using these parameters in the Comsol model. The thickness of the channel, we'll skip that for now also. Spacing between the landing pads. So this basically allows you to determine kind of how far apart the inner versus the outer ones are, and we'll see why this is important later. And then we also have a contact rotation factor. This is another thing that's related to how the contacts are placed, and I'll explain these parameters when we get to the Comsol model. Thickness of spacer, we'll skip these two for now because these are 3D parameters. And then, so then we have the release holes, right? So these are the side lengths of the release holes. These are the number of release holes at each layer. And then basically what we do is we have these kind of circles going outwards containing these release holes. And I'll explain that a little better. It's a little bit complicated, but you can also just figure it out by like playing around with it. So the first thing we do is we create a layout, and then we create a cell, which is our design. Then we define this rotation transformation, which basically just rotates something by some amount, right? Depending on the number of sides that we have. So in this case, this will be a 90-degree rotation. And we actually use this a lot throughout our design because we want to rotate things accordingly. So the layers, we talked about this before. The first layer is, so we also have an edge processor. I'll explain what that is later. The NEM Relay anchor is the first layer. We saw that. The NEM Relay channel is the second layer. Then we have the contacts, the body, the holes, which are basically the release holes. Then we have the substrate. So this is basically the substrate metal, right? So we have some metal in the substrate layer. And then we have the substrate gaps. So this is basically the gaps between the substrate and the landing pads. And then we have the NEM Relay landing pads. So everything here corresponds to a layer in our final design, right? So the first thing we can do is create the anchors. So we just create boxes, what are called boxes for those. And these boxes are centered around some point, right? Which is at, you know, this. And then what we do is we use that rotation and we create one anchor rotated by 90 degrees each time. For the body, what we do is we create the plate, right? Which is this like square, right? So in this case, it's a square. Then we can create the anchor. So we so here, trying to figure out what's going on here. So yeah, so for the relay body, we need to have this sort of this connection to the anchor, right? So we're creating boxes for those. We create boxes for the arms, right? The cantilever arms. Then we create this box for a connection between these two. And then we create the actual like square right in the middle. And then we create that 4 times. We just rotate it 4 times. So that's basically what's happening for the relay body. I won't go too much into detail. You can play around with that if need be. And then here we have the relay holes. So these relay holes are boxes that are created in sort of a circular layouts starting from the middle, and then you just go outwards in circles. And then the number of holes to place at each layer is determined by this list right here called N hole. So it's 1, 8, 16, 24. And you can see that this R hole placement is basically how far to keep spacing it out, right? Yeah, and so that basically is how to do it. All right, yeah, so you can play around with the holes as well. That's another thing you can do. And then the substrate is basically, you first create the plate, right? And then you also have the anchors, right? So we added the anchors up here. So in the substrate layer, the metal that you have in the substrate layer is just the anchor plus the plate, right? And we saw that earlier. Then we have the contact layer and the landing pads. So the contact layer is essentially, it's basically the same thing, right? So you create the contact layer, which is basically the landing pads. And there's also these larger squares that are around it. So this basically creates all of that. And the way it does that is using a technique which is basically you do this offset rotation of circles going all the way around, and then you have an inner circle and you have an outer circle. So you can see that there's one inner circle here and there's an outer circle on the outside. And that's basically how it works. This will be described more in a paper that's to be published soon. So keep an eye out for that. I'll have a link once it comes out in the description as well. All right, yeah, and make sure to cite that paper if you use this model. So here we have the channel layer. And the channel layer basically is, again, these rotations of these little rectangles going all the way around. And we have one for the inner layer and one for the outer layer. And then lastly, we can just write all of this out to a layout file, GDS layout or DXF, which is another drawing format, or the CIF file. So right now it just outputs to all three. So then we can just do Python relay.py, and that actually generates these GDS layouts for us and other types of layouts. And we can just continue to change the length of the side plate. So here we can change it to 4,000, which will make it larger. And we can just rerun this, open relay.gds, and just reload it. And you can see that we get this sort of weird looking structure where the plate is larger, right? But everything else is sort of the same. And this, so this kind of doesn't work. We see that the overlap, there's like overlap, but we could also make the diameter of this larger or something and make it work. And you can play around with all the parameters like the beam width, the beam length, all of those sorts of things can be changed. So now let's get into the Comsol module. So Comsol, before we get started, let's talk about kind of what you'll need. So this works with Comsol version 5.4, and you'll need to have multi-physics, ECAD import module, and the MEMS module. And so what we do is we basically start by importing the relay geometry here. So we first import it from GDS, the GDS layout, right? And so let's take a look at what that looks like when we do that. So when we import from the GDS, we initially have, we take that 2D structure and we extrude it. And so what you can see here is we have, for each layer, we have a thickness and an elevation associated with that layer, right? And the thickness is basically how thick that layer should be. And then the elevation is basically how far, like where you want to start building it at, right? So you see how they start at different locations. And this is really cool because we just start with this layout and we immediately have a 3D model inside of Comsol. And so that's really cool. And of course, all of the thicknesses and elevations are defined in our relay parameters in the global definition section. And you can modify these to change the thicknesses and where things start basically accordingly. So yeah, so these are very important, like the thickness of the poly layer, everything has a description. You can see what those mean internally. So let's talk about what we need to do after we have this import. We actually have a few more steps. So we first need to remove the body holes, obviously. So now you can see that we've cut out holes from the thing. We need to create a substrate. So this basically is when we're modeling the electric fields, we need to have the kind of the surface that this relay is on. We can remove the gaps. This will basically remove gaps at the bottom, which is pretty important for making the spacer between this. We remove this metal from the substrate dielectric. There's a bunch of steps here, and delete the old substrate. Then we need to split the body plane. So what this does is we create this plane, right, that goes across, and it actually is, it splits the body into a dielectric part and a polysilicon component, right, which is the conductive part. So we have these two parts, and so this plane defines where that split happens, and then the partition happens in the next part. So that's where here's where the split happens. And then we define what the poly layer is. That's just this box selection, right? And then we actually need to cut that. So when we cut this, we basically, what we're doing is we're cutting out the plate, and you'll see what happens. You see how there's now a line here, and now we have this plate section. And this is actually where we apply a force when we have the spring constant analysis later. Then we partition the body, the poly into that domain, basically. And then we wrap the whole thing in this spherical enclosure. And this basically is modeling the universe. We usually keep this grounded in our electrical analyses. And what the purpose of that is basically to, outside of this sphere, right, everything is zero potential. And that just makes it easier for Comsol to model everything. And it also gives you a reference for all of your studies that you're doing. Okay, so now let's talk about the materials. Materials are basically, you need to define properties for each of these. So we use air as the ambient. The body is made of polysilicon germanium. The contact channel, which basically connects the source and the drain, is made with tungsten. The dielectric material we're using is aluminum oxide. The substrate metal is aluminum. And then we have landing pads with tungsten. And lastly, we have the substrate dielectric, which will be kind of, should be in your CMOS back end of line, right? So this will be silicon dioxide. We're just pretending that we're doing this on like some sort of silicon substrate at the end of the day. Great. Okay, so now we've talked about the relay geometry and the materials. And so now we want to, I think the best thing to do now is to jump into the studies and talk about what's going on. So in the spring constant, we have, this is the first analysis and it's the most basic. And this is called a static analysis, stationary analysis. And essentially what we're doing is we deactivate all of the different physics phenomena, except for the mechanics, right? So all we want is we want the solid mechanics, which is basically, so we're trying to figure out the spring constant of this. So we don't care about all the electrical properties yet. And so in order to do that, we deactivate everything, all of these physics, except for one. And the one that we keep is we keep the solid mechanics quasi-static. And this is basically, is just defining how we can bend this relay essentially. And so, yeah, all you need here is the linear elastic. So we'll go into the quasi-static and take a look at what's actually going on there. So we have the linear elastic material relay. This basically allows you to bend the relay in the physics. Free basically just means everything is free to move. But then we also have this fixed constraint on the anchors, right? So that we hold the anchors in place, right? The anchors are stuck. And so the rest of the relay is allowed to move except for the anchors, right? And then lastly, we have this boundary load. This is basically the force that we apply onto the relay plate. Remember we created that plate earlier? And so we're just applying a force on this area, the red area selected here, and it's going downwards. And this will allow us to actually come up with the spring constant. And the result of this, well, you can look at it in the results section. So once you've run, you can just right click on this and say compute. I won't do that right now, but we have the results. It basically produces spring constant solution 1. And then you can look at mechanical properties. And if you look at Eigen Modes, you'll see, sorry, if you look at spring constant, you'll see that if you evaluate this, you should see the spring constant pop up here. So this basically you'll see if you scroll down, there's a force to apply for the spring constant and you divide that by the displacement, right? And that gives you the spring constant, which is here is 26.269 newtons per meter. We also get the proof mass, which is basically just done by integrating the density of this relay over its volume. Yeah, so that's the first analysis. Then we'll talk about modal analysis. So this is a frequency domain analysis, which basically allows you to compute the Eigen Modes of this relay, which are basically the directions in which it'll move and things like that. And you can get the shapes of these and you can get the frequencies at which these occur. And so the modal analysis just works again with the same, so we deactivate everything except for just the solid mechanics, right? Because we're doing pretty much the same thing. So if you look at this, we deactivate everything except for solid mechanics, quasi-static this one. And essentially what this allows is it gives you, so also we remove the boundary load because we don't need that in this case, but basically we're just vibrating this relay and seeing which are the ways in which it vibrates. That's kind of a rough picture, not completely accurate of what's going on here. But anyways, what you can get here is you can get the mode shape. So the mode shape will show you how the relay is moving, right? And you can look there, it gives you 6 mode shapes, so you'll be able to see them if you just change the frequency at which you're plotting, and then you should be able to see different mode shapes. So this one is a kind of a tilty one. And then you can also just look at the frequencies themselves. That's in the Eigen Modes mechanical properties. And this basically tells you kind of like how the relay's motion is affected by different things in your system. Great, so now let's talk about parasitic extraction. So parasitic extraction, we want to extract mutual capacitances between different components of the relay. And so essentially what we do is we do a stationary source sweep. And what this is basically you ground everything except for one component, like terminal in the system, right? So the terminal could be the source, the drain, the landing pad, the gate, the body, anything basically could be a terminal. And basically what you're trying to do is you're trying to say, hey, what's going to happen to the system when I change, what's the capacitance between these two components when I set this one to 1 volt and this one to 0 volts. And basically it uses this, it models all the electric fields. So this is very accurate compared to other approaches for modeling the capacitance. This is pretty much the most accurate you're going to get using the finite element method. And so here you have a stationary source sweep. This will basically, you can see it says RLC. So here we're extracting mostly the C's, the capacitances. And in this step, we actually deactivate everything except for, so we don't have any movement, right? So we deactivate everything except for parasitic extraction, essentially. So you can see that all of these ones are gone, right? And the only one that we're actually computing is parasitic extraction. And what this does is it basically sets voltages to 0 for everything and uses the charge conservation property. And then it basically will do for each one, it'll basically sweep across all of the terminals and figure out what the capacitance is. And what you get is you actually get this capacitance matrix. So it's called the mutual capacitance matrix. And each number corresponds, so each element of this matrix corresponds to, I guess each row and each column corresponds to one of the terminals in the system. And you can figure out which terminal it is by looking at the terminal number and the mutual capacitance to that terminal on the other side, right? So it's basically symmetric along the diagonal. But this is cool because now you can use this in your SPICE modeling, which you might want to do later, and is in also the repository that I have. And yeah, you can basically use these mutual capacitances for a SPICE model. Yeah, okay, so that's the parasitic extraction study. Now we'll talk about the quasi-static sweep. So the quasi-static sweep is actually, what you can do is this will basically sweep the gate voltage, and what you can do is you'll actually get the displacement curve of the NEM relay. So you'll see something like this, right? And you can see, so here we have the pull-in phenomena, we have this hysteresis right here, and we have the pull-out phenomena right here. And this is really cool because this is how a NEM relay works in pull-in and pull-out mode. You usually see these kinds of effects. So you can see the pull-in voltage is around like 5.5 volts or so. And the pull-out voltage is around a little below 2 volts. Yeah, this is super cool. But basically the way this works is we deactivate most of them, except we want to keep, so we keep electrostatics. We disable the parasitic extraction. We keep this solid mechanics. And we also have this multi-physics coupling, which is the electromechanical forces. And you need the MEMS module in order to do this. But this couples the electric domain to the mechanical domain. It allows you to do things with like Gauss's law, basically. Sorry, Coulomb's law. Yeah, so here we basically have the Coulomb attraction between all of the different components in the system. And it's very accurately modeled, as opposed to things like, I originally tried to do this in ANSYS and realized that you can't do very accurate sorts of modeling of these, of the interactions between the electric fields and mechanical action. So yeah, so essentially we just use this. We of course disable the boundary load. We only use that in the spring constant one. And then we also have this electrostatics, which basically will change. Basically we sweep the electric potential on the gate, right? And we ground essentially the body. That's basically, and we have everything else floating. And then we basically see that the body like comes down or comes up based on the potential that's going through. Yeah, and so that's how the quasi-static sweep works. And you can also see the electric potential. There's like this nice plot which actually shows what the electric potential looks like. And you can see that there's, this is how the electric fields are modeled. You can actually see that, and it's really cool. And then lastly, we have the transient sweep. And so the transient sweep is basically showing you how fast the relay moves, right? So in order to do that, we keep the electrostatics active, and then we also have the solid mechanics transient physics active. And then we also have the coupling between those two. So we have the multi-physics coupling, and we use a separate one for that. And essentially when we put all this together, you actually should get the transient displacement curve. So this shows how the relay pulls in if you put it at like 10 volts to start with, right? So here it just goes zoom, and it goes up to the top, and it gets stuck up there. And that's kind of how you expect the pull-in to happen. And so you can see here that the relay pulls in 20 nanoseconds. And so that's very cool. And there's no damping involved in this, this one. And so that's basically an overview of how to use this NEM relay model in Comsol. And I hope this is useful to you. Yeah, please reach out to me if you have any feedback, if you have any improvements to the model, if there's anything you'd like to see in a future version, if there's anything that's not working for you. Yeah, just let me know. I'm happy to help. I really want other people to be able to use this model. I think the point of research is to you know, improve understanding in the world out there. And so I'm hoping someone else besides me is going to use this model at some point. All right, thank you so much. And good luck with Comsol and KLayout. Thank you.